Fracton self-statistics is a novel concept in the study of quantum phases of matter, characterized by quasiparticles with restricted mobility, known as fractons. Unlike topological orders, fractons cannot move without creating multiple excitations. A fundamental question in this field is whether the notion of self-exchange statistics can be naturally defined for fractons, given their complete immobility as isolated excitations. In conventional topological orders, emergent quasiparticles in 2D quantum many-body systems can exhibit anyonic statistics. However, fracton systems have emerged as an active frontier of quantum physics, attracting interest from condensed matter, quantum information, and quantum field theory viewpoints. This work resolves the puzzle of fracton self-statistics by allowing the fracton quasiparticle to split into multiple coordinated pieces, enabling the preparation of two well-separated realizations of the same fracton superselection sector. This concept applies to both fracton phases of foliated and fractal nature. The authors derive general constraints satisfied by the fracton self-statistics in a large class of Abelian fracton orders. They also provide explicit examples by distinguishing twisted checkerboard models and a twisted Haah's code from their untwisted counterparts. This demonstrates that fracton self-statistics is a fundamental invariant needed to characterize fracton phases of matter. Foliated fractons, which are Abelian and satisfy the fusion constraint, are used as a concrete example. The checkerboard model is defined on a 3D checkerboard lattice with 1 qubit per vertex, with its Hamiltonian given by HCB equals XC, AC plus BC. The authors establish that fracton self-statistics is a key part of the characterization of fracton orders, providing a fundamental invariant needed to distinguish between different fracton phases. This work opens up new avenues for exploring the properties and applications of fracton systems, which have the potential to exhibit unique quantum phenomena. Future research directions include exploring the self-statistics of non-Abelian fractons and investigating the experimental realization of fracton systems. Foliated fractons, a novel type of quasiparticle, exhibit mobility in two-dimensional subspaces. They are characterized by their ability to move in certain directions, which can be described using a 3D checkerboard lattice model. The paper highlights the self-statistical phases of these fractons, denoted as theta, xyz, a, theta, xyz, a, theta, xyz, a, and theta, xyz, a, with a constraint that their product equals 1, leaving only 3 of them independent. Calculating these phases involves the use of windmill exchanges, sequences of 6 membrane operators that result in the exchange of a fracton A with another fracton B within the same superselection sector. These exchanges are visualized through diagrams depicting the starting and ending states of the process, as well as the intermediate steps involving membrane operators. The paper also introduces the concept of mutual braiding statistics between dipoles, represented by S micro ab, where micro represents the direction of braiding. This quantity is defined as the statistical phase acquired when 2 dipoles, each consisting of a pair of fractons, are braided around each other in the direction specified by micro. The paper demonstrates how the self-statistical phases can be related to the mutual braiding statistics, providing an equation that connects the two concepts. This connection is crucial for understanding the behavior and properties of foliated fractons, and their potential applications in the study of topological quantum computing and other areas of condensed matter physics. The authors provide a graphical proof of the statistical phase theta, xyz, associated with a deformable fracton A, which can be transformed into 3 steps using operators supported on different areas. This relation is utilized to derive equation 4 through a 180-degree rotation about the axes and multiplication with equation 5. The mutual statistics of 2 fractons, A and B, are also derived, yielding equation 6, which generalizes the constraints of 2D Abelian topological orders. For an Abelian planon satisfying the foliation condition, the discussions reduce to familiar 2D equations. The self-statistics of a foliated fracton satisfying an equals 1 are constrained to discrete values, which can be used to distinguish fracton orders. Notably, the self-statistics of A are multiples of E2 pi I, NGCD, N2, analogous to those of anyons in 2D. The authors apply these results to semionic fractons in twisted checkerboard models, demonstrating that the 8 models considered fall into 2 quantum phases distinguishable by the presence or absence of semionic Fracton self-statistics. Specifically, the model HXCB, constructed using a non-Pauli stabilizer Hamiltonian, exhibits semionic Fracton self-statistics, distinguishing it from the untwisted model HCB. The authors provide an explicit construction of the twisted model HXCB, including the definition of the stabilizer Hamiltonian and the twisting factor, which leads to semionic self-statistics for Fracton excitations. These exotic self-statistics are exclusive to fractons and cannot be realized by tensor products of 2D anion models, highlighting the novelty of HXCB as a distinct phase of matter, referred to as a semionic Fracton order. Fracton self-statistics in various models, including Haah's code, are explored, demonstrating that twisting can be applied to multiple directions simultaneously, resulting in different ground states. Despite these differences, certain models, such as HXYCB and HCB, represent the same semionic Fracton phase. The Haah's code, an exactly solvable model defined on a cubic lattice with 2 qubits per vertex, is examined in detail. The model's Hamiltonian, Haah, is described, and excitations are represented by polynomials. Excitations can travel arbitrarily long distances in certain directions, termed mobility cones, which are used to categorize fractons in the Haah's code into 3 types: A, B, and mixed. Windmill self-statistical processes for these fractons exhibit purely bosonic self-statistics. A gauge-theoretic variant of the Haah's code is also considered, where excitations become fermionic due to the introduction of fermionic modes. Fracton self-statistics are used to resolve the question of whether this twisted Haah's code represents a distinct Fracton order from the original Haah's code. It is found that attaching bexcitations to excitations changes their mobility, making it impossible to compensate for the statistics change. This result contrasts with the 2D toric code and the checkerboard model, where attaching bexcitations can compensate for the statistics change. The Haah's code and its variants exhibit distinct Fracton self-statistics, providing a deeper understanding of Fracton behavior in these models. The introduction of fermionic modes in the gauge-theoretic variant leads to a change in the statistics of excitations, which cannot be compensated by attaching bexcitations. This work contributes to the understanding of Fracton self-statistics and their behavior in various models, highlighting the importance of considering the interplay between Fracton mobility and self-statistics in the study of Fracton orders. Fracton superselection sectors have been extensively studied, with a focus on self-statistics, a crucial concept in characterizing Fracton orders. The authors demonstrate that 2 realizations of a Fracton superselection sector can be exchanged via fractional mobility, paving the way for a comprehensive algebraic theory of fractons. This work is applied to a family of twisted checkerboard models and a twisted Haah's code, revealing a novel phase of foliated nature, dubbed semionic Fracton order. This order is characterized by emergent fermionic fractons, distinguishing it from Haah's code. The key difference lies in the presence of fermionic type A fractons in Haah. The authors' findings contribute to a deeper understanding of Fracton orders, shedding light on their algebraic structure. This research was made possible through collaborations with experts, including Shengjia Huang, Juven Wang, and Ashvin Viswanath, as well as funding from the Natural Sciences and Engineering Research Council of Canada, the National Natural Science Foundation of China, the U.S. Department of Energy, and the Simons Foundation. This study provides a foundation for future work, addressing the complex properties of fractons and their potential applications. The author's approach opens up new avenues for exploring Fracton orders, with implications for our understanding of topological phases of matter. The authors provide a comprehensive review of existing research on Fracton orders, subsystem symmetry, and topological phases, citing various works on designer non-Abelian fractons, subsystem symmetry enriched topological order in 3 dimensions, and non-Abelian hybrid Fracton orders. They also reference Fracton models on general 3-dimensional manifolds, renormalization of Ising CageNet models, and Jordan-Wigner dualities for translation invariant Hamiltonians. The authors discuss the assumption of orthogonal axes in their paper, noting that oblique axes can be considered in general. They draw on research on symmetric Fracton matter, twisted foliated Fracton phases, and strong planar subsystem symmetry protected topological phases. The concept of twisted Haah's code and the discreteness of Fracton self-statistics are also highlighted. Understanding the interplay between different fractional mobility structures and their constraints on Fracton statistics is emphasized as an important area for future studies. The authors reference works on quantum error correction with the Semyon code, non-Pauli topological stabilizer codes, and the Y-cube model with fractal structure of subdimensional particles on hyperbolic lattices. Building on previous research on string net condensation, twisted quantum double models, and Pauli stabilizer models of twisted quantum doubles, the authors introduce the concept of non-Pauli stabilizer formalism. They provide expressions and properties of elementary string operators, which are useful for various purposes. The authors also draw on research on local unitary transformation, long-range quantum entanglement, wave function renormalization, and topological order. This comprehensive review provides a foundation for understanding the complex relationships between Fracton orders, subsystem symmetry, and topological phases, highlighting the importance of continued research in this area. The supplementary material provides additional details and proofs for the main text on Fracton self-statistics, focusing on two key sections. Section SI delves into counting windmills for foliated fractons, identifying 8 distinct windmill configurations, denoted as XYZ, which can be divided into two groups of 4, with the latter being spatial inversions of the former. These configurations are specific to foliated fractons as defined by equation 1 in the main text and do not exhaustively cover other scenarios, such as fractal cases or variants. Section S2 presents a proof for equation 6 in the main text, relying on the observation that theta xyz q times q can be decomposed into theta xyz q and theta xyz q when excitations q and q are separated in the 111 direction. This is illustrated in figure S1, which demonstrates that theta xyz q times q can be realized as a composition of xyz processes for q and q on two parallel windmills that do not intersect. By leveraging this observation, the authors derive equation S1 relating the self-statistics of A times B times LMA times minus LMB to the self-statistics of A times B, LMA, and minus LMB. Additionally, they obtain equations S2 and S3, providing alternate expressions for the self-statistics of A times LMA and B times minus LMB in terms of statistics of A times LT micro A and B times minus LT micro B, respectively. These equations are pivotal in establishing the connection between self-statistics of various configurations. Notably, these results build upon the foundational equations in the main text and are instrumental in understanding the properties of fractons. However, the scope of this analysis is limited to foliated fractons, and other scenarios, such as fractal cases or variants, remain a subject for future investigation. The double Semyon model, a topological phase, is formulated mathematically and represented in a non-Pauli stabilizer formalism. By establishing the reducibility of windmill processes into bratings of planons, the topological invariant theta xyz A times B times LMA times minus LMB is expressed in terms of individual braiding self-statistics and mutual statistics. The identity theta xyz A times B equals theta xyz A theta xyz BSX ab psi ab SZ ab is proven by comparing equations S1, S2, and S5, revealing crucial insights into the topological properties of the double Semyon model. The 2D double Semyon model is then formulated in a non-Pauli stabilizer framework, starting with the twisted Z2 gauge model representation. This is transformed into a non-Pauli stabilizer code using the substitution as equals BOS, PBs, which is essential for the development of twist checkerboard models. The flux term Bs and gauge transformation as at site S equals 4 are defined, and their commutation relations are derived. The projective representation of Z2 is established when Bs equals 1, demonstrating the substitution's role in converting the double Semyon model into a non-Pauli stabilizer code. The 4 possible states at each site S, labeled by as Bs equals 1, 1, 1, 1, I, 1, and I, 1 are examined, with 1, 1 being the trivial state. Self-statistics of these states are determined, revealing trivial self-statistics for the trivial state and non-trivial self-statistics for the other states. These results are derived using mathematical tools specific to topological quantum physics, assuming a high level of familiarity with the subject matter. The mathematical framework established here provides a foundation for understanding the topological properties of the double semyon model, which is essential for the development of more complex topological quantum systems. Although limitations and assumptions are not explicitly stated, the focus on mathematical formulation implies reliance on the assumptions of underlying topological quantum field theory. Future work is expected to apply the non-Pauli stabilizer formulation of the double semyon model to more complex systems, as hinted by the development of twist checkerboard models. The double semyon model, a topological code employed in quantum computing, is presented on a 2D checkerboard with qubits located at each vertex and sites holding fluxes. To analyze excitations within the system, operators A and B are defined, with a focus on three excitation types: A, B equals 1, 1, A, B equals 1, 1, and A, B equals 1, 1. Each type's creation, movement, and statistical properties are thoroughly explained using detailed equations. The semyon excitation, A, B equals 1, 1, is movable using string operators such as S's or S's, which flip the state of qubits along a path of edges. Its self-statistics are determined by performing a counterclockwise exchange of two such excitations, resulting in a phase factor of I. This calculation involves applying identities related to the S's operators, including S24S47S14 equals S24S14S47B4 equals Is14S24S47B4 equals Is14S47S24. The excitation type, A, B, equals 1, 1, is a bound state of the previous two types, created in pairs and moved using operators S. Its self-statistics are calculated to be I through a similar computation as for the semyon, with S's replaced by S. These calculations provide essential insights into the statistical properties of the double semyon model, with potential implications for quantum computing applications. The construction of twisted checkerboard models is a crucial aspect of the research. A correspondence is established between the double semyon model and each layer of 3D twisted checkerboards, as illustrated in Figure S2. This correspondence enables the expression of twisted X operators, which are explicitly given in section SIVB. On the double semyon side, a 2D checkerboard with qubits labeled by D is considered. The configuration of all qubits in the Z basis is denoted by Z, D. A product of four Pauli X operators, as, acts on Z, D, and assigns a U1 phase, phi S, Z, D, associated with the change of Z, D, under as. Similarly, S's in equations, S12, and S13, can be viewed as a modified X operator of the form X sigma equals X SGs. Z, D, with G's, Z, D, element of U1. On the 3D checkerboard side, each layer corresponds to a 2D checkerboard, with edge variables ZL mapped to vertices and gray, blank, cubes to gray, white, squares. The change of edge variables under AC or XV is analogous to that of Z, D, under as, with associated U1 phases phi C, Z, E kappa n, and gamma V, Z, E kappa n, respectively. The twisted checkerboard model HXCB is obtained by twisting all X layers, where AC right-pointing arrow XC equals AC phi XC and XV right-pointing arrow XXV equals XV gamma X versus the algebraic properties of XC and XXV can be derived, enabling the analysis of HXCB as a non-Pauli stabilizer code. Explicit expressions for XC and XXV are obtained based on the correspondence between Xn and D in Figure S2b. For instance, XC can be expressed as XC equals AC phi XC equals AC phi 1 plus X, XC phi, 1 plus x, xcd, where phi 1 plus x, xc and phi 1 plus x, xcd denote the twisting factors associated with the x layers containing x edges whose vertices are L equals 1 plus x, xc and L equals 1 plus x, xcd, respectively. The twisting factors phi x underscore c and gamma x underscore v are derived from the twisting factor of EQ. S24, by replacing z underscore v with edge variable z underscore lv equals z underscore xc z underscore cv for L equals 1 plus x, xc. These twisting factors are used to define the twisted checkerboard models, such as h underscore xy underscore c, obtained by replacing a underscore c right pointing arrow a underscore xy underscore c equals a underscore c phi underscore x underscore c phi underscore y underscore c. The twisting factors phi underscore y underscore c and gamma underscore y underscore v along layers and z layers are obtained from phi underscore x underscore c and gamma underscore x underscore v by a threefold rotation that permutes x, y, and z directions. The authors demonstrate that the excitation of h underscore x underscore c, denoted m underscore x, is a semionic fracton through two derivations. The first approach involves working out the details of the twisted x operator for generating fractional moves of excitations explicitly. Using EQ, S21, and the E underscore x caret nd correspondence in Fig. S2, b, the authors obtain the expression for x underscore v in EQ. S26. They then derive the commutation relation x underscore v x underscore v in EQ. S29, by direct computation, which establishes the semionic fracton self-statistics of m underscore x. The second approach provides a fast and intuitive way to write down fracton self-statistics in twisted models. By considering a model h underscore x underscore c obtained by twisting the checkerboard model along x layers only in the x greater than 0 region, the authors show that the self-statistics of m underscore x and h underscore x underscore c can be obtained from the self-statistics of b underscore plus and b underscore, where b underscore plus or minus denotes 1 b underscore c equals 1 excitation of h underscore x underscore c at plus or minus L for L greater than 0. The authors then use EQ. S6 to derive the self-statistics of m underscore x in EQ. S31, which simplifies the computation of theta, tau, underscore m underscore x. The authors note that the idea of the second approach, which simplifies the computation of a fracton statistics by combining twisted and untwisted phases, applies to other twisted models of foliated fractons. The derivations presented in this section demonstrate the semionic fracton self-statistics of m underscore x and h underscore x underscore c, which is a key result in the study of twisted checkerboard models. Classification of twisted checkerboard models is achieved through local unitary transformations, with two gapped models belonging to the same phase if and only if their ground states are related by such a transformation. The authors demonstrate this by finding a local unitary transformation connecting hxy underscore c band hcb. They utilize the x underscore nd and ey underscore nd correspondences for twisting construction, denoting the resulting model as hxy underscore cb. This model differs from hxy underscore cbby, a local unitary transformation. The twisted x operator takes the form xc underscore v equals xv gamma x underscore v gamma y underscore v, where gamma x underscore vand gamma y underscore var related by the reflection that swaps x and y. The authors show that xc underscore vand xc underscore van to commute for versus equals xy plus or minus 1v and commute otherwise, leading to the existence of a local unitary transformation U that maps xv to xv while keeping zv fixed. The explicit form of U is given by equation S33. This transformation implies that the ground states of HCB, hxy underscore cb, and hxy underscore c bear related by local unitary transformations, and they all belong to the same fracton phase. Notably, twistings in two different directions are related and can even cancel each other through a local unitary transformation. The concept of mobility cones is crucial for understanding the behavior of quasiparticles, especially fractons, in a gapped phase. In Rho, a set K is called a cone if alpha V is in K for all V in K and alpha in R is greater than or equal to 0. A cone K is called convex if alpha 1 V1 plus alpha 2 version 2 is in K for all version 1, V2 in K and alpha 1, alpha 2 in R is greater than or equal to 0. The conical hull of a set south in Rho is defined as the set of all conical combinations of S, denoted as cone S. Let E3 be the Euclidean space where physical degrees of freedom live, and R3 be the group of translations. For K in R3 and C in E3, C plus K is defined as the set of all X plus V, where X is in C and V is in K. The notion of mobility cones for quasiparticles in a gapped phase is then defined, providing a mathematical framework for understanding quasiparticle behavior. In the context of superselection sectors, a mobility cone is defined as a closed convex cone K in R cubed, allowing quasiparticles in a sector Q to move to infinity within the conical region O plus K. 3 examples illustrate the properties of mobility cones, demonstrating that the empty set is a mobility cone for the trivial sector, while cone X and cone X are mobility cones for quasiparticles with conventional mobility along the X direction. Fractons, however, exhibit no conventional mobility, resulting in only 2- or 3-dimensional mobility cones. The invariance of mobility cones under local unitary transformations is established, ensuring that if K is a mobility cone for a sector Q, it remains a mobility cone for the transformed sector Q. This property is crucial for understanding quasiparticle behavior under local unitary transformations. In the Haah's code, excitation patterns within finite regions are labeled by A, B, element of R squared, with A and B specifying the configurations of A-term and B-term excitations, respectively. 2 patterns, A, B, and A, B, belong to the same superselection sector if and only if A, element of I and B, element of I, where I is an ideal of the group ring R. This leads to the classification of superselection sectors into type A, type B, and mixed. Type A and Type B superselection sectors are distinguished by the values of QA and QB. The ideal I equals F, F, R describes the fractional moves of A-term excitations and can also be generated by F and G equals Y plus Z, F plus F equals Z squared plus Y plus 1, Y plus Y squared plus Y plus 1. This results in the identification of 2D mobility cones K, K, and K for type A superselection sectors, with their spatial inversions K, K, and K being mobility cones for type B superselection sectors. The distinction between type A and type B superselection sectors by mobility cones is supported by the demonstration that none of keys, respectively, keys, is a mobility cone of any type A, respectively, type B, superselection sector. This is achieved by showing that the cone K is not a mobility cone for any type A superselection sector, using the invariance of I equals F, G, R under 2 transformations. The mathematical framework for understanding the ideals I and the mobility cones K, K, and K is provided by equations S36 and S37. Figure 5 of the main text offers a visual representation of these mobility cones. Notably, 2D mobility cones along the YZ plane suffice for the current purpose, although considering 3D mobility cones is also possible. In the Haah's code and its twisted variant, the excitation self-statistics are analyzed by considering an exchange process between 2 excitations, denoted as A and B, initialized at different locations within the lattice structure. This exchange process, theta A, involves a series of fractional moves along the YZ plane, leveraging the property of the operator F1 equals 1 plus X plus Y plus Z, which enables a fractional move from the YZ plane to any X equals N plane for N equals 1, 2, 3. To bypass the origin, the exchange process is deformed using detoured paths, ni, analogous to the original paths, mi, for B. This deformation transforms theta A into a trivial process, resulting in theta A equals plus or minus 1. The discreteness of theta A is crucial for distinguishing Fracton orders in the Haah's code and its twisted variant, as it allows for a precise characterization of the discrete values of Fracton orders. This analysis provides a fundamental understanding of the self-statistics of excitations in these codes, highlighting the significance of theta A in determining their properties. In Haah's code and its twisted variant, excitations exhibit mobility along tetrahedrons, enabling their movement in specific directions within the lattice. This property, illustrated in figure S3, is a direct consequence of the twisted variant's topological properties, which introduce nontrivial topology to the system. The twisted variant allows for the creation of exotic topological excitations, such as excitations that exhibit non-Abelian statistics. The movement of excitations can be mathematically described using topological quantum field theory, where they are represented as defects in the lattice, characterized by their topological charge and statistics. The mobility of excitations is encoded in the braiding statistics, which dictate how the defects interact with each other. Understanding the movement patterns of excitations is crucial for developing novel quantum error correction strategies. By carefully controlling the motion of excitations, it may be possible to mitigate errors that arise during quantum computations. The topological structure of Haah's code and its twisted variant, discussed in previous sections, enables the movement of excitations along tetrahedrons, which has significant implications for quantum error correction. However, a limitation of this work is that it assumes a perfect lattice structure, neglecting the effects of disorder and noise that are inevitable in real-world implementations. Future work should focus on developing strategies to mitigate these effects and enhance the robustness of topological quantum codes. Figure S3 serves as a visual anchor for the theoretical concepts discussed in the paper, providing a concrete representation of the topological properties of Haah's code and its twisted variant.